Hello everybody, today we are going to solve another daily LeetCode challenge, problem number 329, longest increasing path in a matrix. So the problem is we are given m by n integer matrix and the task is to return the length of the longest increasing path in this matrix. So here are a few rules. We can always move in 4 directions, not diagonal. So this is in matrix, this is a 4-directional problem. So we can always move top, right, bottom, left. And while we are moving, the only valid moves are the moves that the value is increased. For example, if you see here, when you are starting from this node with a value of 1, while we are moving, so the values are always increasing. So this problem, you can consider this problem as finding the longest path in a directed graph that doesn't have any cycle. So we can prove that this is a directed graph without any cycle. And in order to prove that, we can do that by contradiction. Consider if there exists a cycle in a graph and we are starting from u1, so we have u2, u3, and un, and then this is the cycle, and then from un there exists an edge from a u1 that the cycle that creates a cycle. But at the same time, we know that the only valid edges are those edges that the values are increasing. So that means the value of u1 is less than the value of u2, the value of u3 to un. So if I represent them by v, so v1 is less than v2 less than up to vn. And at the same time, since there exists an edge, so vn must be less than v1, which is not possible. So we are sure that there is no cycle in this graph. In order to solve this problem, we can use a DFS for traversing a tree, and then initially we create another matrix and for each node we store the longest path possible from that specific node. So for example, we are starting from the top left, and then from node 9 we check the neighbor, the adjacent cells, and since there is no valid cell, 2 of them are beyond the boundary of the matrix, and the other 2 has less than or equal value. So the longest path starting from 9 would be 9. We repeat that, so for this node as well, and from 4, starting from 4, there are 2 valid moves from left or bottom, and recursively, since we are running the DFS, so we are checking this function, the DFS function, for all valid neighbors, and then compute the maximum value of the neighbors plus 1. So in this case, starting from 4, since we already computed the value of this cell, so we have a candidate of value 2, so 1 plus the value here would be 2, and then we call the recursive function on this node on 8. So node 8 check the neighbors, and since the only possible moves are those moves that the values are increasing, we don't have to store any visited value here in this time, because if we consider a parent-child move in a graph, when we are moving from a parent to a child, we know that the value of p is definitely less than the value of child. So the other way is not possible. So we don't have to be worried about that. And then on node 8 here, one of them is beyond the boundary of the matrix, and 2 of them has less value. So the value, the longest path value for this cell would be 1. So, and then on returning onto node 4, this is 1 plus 1, again 2. So the final value for node 4 is computed as 2. We'll repeat this procedure until we eventually visit all cells in this matrix, and at the end, since we are asked to find the length of the longest increasing path in the matrix, we just compute the maximum value in this matrix, which we stored the maximum length value for starting from each cell separately as the result of the problem. So let me implement that, and we can see what is the solution here. So first of all, we are given an m by n matrix. So let's store those values. M and n equal to length of the matrix and the length of matrix 0. And for longest path, we need to store the values. So I define it as L path. L path stores longest path starting from each cell, and it is initially as, let's say it's an m by n initially, an m by n matrix, all with 0 values. So for that, times n or in range m. So this is an m by n, so we initialize that. And then we need to define our traverse function. It is quite similar to DFS, but since there are some differences, I define it as traverse. And then from, this is the node that we are starting from. And first of all, we need to check if it is already computed in the previous iterations. So with that, we can check if the L path for I and j is already greater than 0, simply return it. So we don't have to do the recursion again. Otherwise, let all paths equal to L path of the current cell that we are visiting. Let's put that to 1, so that if there is no valid cell, at least we are able to visit the current cell that we are at. So it is at least 1. And then for neighbors, for adjacent nodes, how to compute that? We have 4 different directions. Since this is a 4-directional problem, as you remember in the previous problems, we used to define the direction so that if in the future the problem changes to a 8-directional problem, for example, the diagonal moves are valid, we don't have to change the structure of the code. So we can simply just change the directions. So valid directions is a tuple of 4, 0, -1. These are the 4 valid moves from each cell. 1, 0, and -1, 0. And for the direction in I and the direction in j in valid directions, the adjacent indices would be I plus di and j plus dj. And so let's first check if this is not beyond the boundary of the matrix. So if than m and j less than m, and this is a valid move, that means the value of the neighbor node is greater than the value of the current node that we are at. So the matrix ij is actually less than the matrix value of ai aj. So this is a valid move. So we should update this path. So we are calling the traverse function for that ai and aj, but since it takes one move from the current cell to the other one, so it would be 1 plus, and then this is the value that we can obtain by visiting that node. So we should update the L path as the maximum of the L path if we could from the current node or from other neighbors, and the value of 1 plus visiting that specific node. So for example, if the cell is in center, we check all 4 directions. If any of them are valid, we just call the traverse recursively, and then each of them report a value, and then we simply compute the maximum of those values plus 1. And this is what is happening here. And then at the end, return L path I and j. So this is our traverse function. And but initially, there might be cases that we trap in some cases. For example, if we start from here, we might be able to visit all cells in the matrix, but starting from none, we would be trapped. So we should iterate through all row by row and visit every cell and call the traverse function on if the L path is 0, so that means it is not visited yet, for I in range M and for j in range M. If the value, the L path value of that ij is actually equals 0, that means it hasn't been visited yet, then we call the traverse function on ij. And then at the end, when the code finishes, we should just compute the maximum value in the m by n matrix that we have here, the L path. So the result at the end, we simply just return the maximum of the every row. So we have a couple of rows. So instead of iterating using for range, so I would run similar way that we use like for each in C# or Java, for example. So in Python, we can simply say the maximum of row for each row in the L path. And also, there's a from my point of view, there's a more beautiful way of having two for loops here by importing either tools. And then instead of that, we can say for I and j in iter tools, the product range m and range n. So instead of these two for loops, this is a dot. This is producing a dot product of two arrays here, but these themselves are iterators, so it is iterating through all of them and then compute the product. So it is similar to writing two for loops, but the beauty of that is that if we have another variable in the future, like ijk, so we can just add range, I don't know, L, for example, in the future, without changing the structure. The computation time is still the same. It is just for the sake of improve the readability of the code. But anyhow, so if it is not, so we call the traverse. So that's okay. Let's debug that. If the L path is 0, and then so there is one value that we are missing here. So initially, if L path is greater than 1, we're just returning it directly, and then otherwise we initialize it with 1. And if the adjacent matrix value is greater than L path equals, and then you're traversing and returning the maximum value. Okay, let's take the second test case first to see if we are always returning a one less value. Okay, so for this one, that's right. But let's see what's wrong with this test case. So before returning that, it is a good idea to print the L path matrix to see. For row in L path, just print row to see what have we computed in row. So for this matrix, and this is the longest path that we find. Okay, and as you can see, these are right, but this portion is not right. And it's supposed to be 1, 2, 3, 4, but we have 3, 1, 1, 1. So let's see, the directions are 0, 1, 0, minus 1, 1, 1. So the directions are correct. And for di and dj, if ai less than m, oh, I missed this, there it needs an equal. Okay, there we go. So let me remove the printing. Also, since it is always check the edge cases, since it says m and n could be equal to 1, let's create a test case that has only one cell. Okay, let's submit that. There we go. So we got almost 600 milliseconds, which is fair and faster than 54% of Python online submissions. Okay, so that was everything for today.